What do an ancient Greek philosopher and a 19th century Quaker have in common with Nobel Prize-winning scientists? Although they are separated over 2,400 years of history, each of them contributed to answering the eternal question: what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of 4 elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom.
Around the year 1911, a British physicist, Ernst Rutherford, carried out the famous gold foil experiment. He did this to understand the structure of an atom. The experiment was carried out by Rutherford along with Hans Geiger and Ernest Marsden. The experiment he performed was a breakthrough in the field of chemistry which helped him understand the structure of an atom in a more accurate manner. This is how the setup of his experiment looked like. As we can see here, he used a source of alpha particles locked in a lead container with a very small slit. This ensured that the alpha particles only came out through a small opening and travelled in a straight line. But why did he select alpha particles in the first place? Well, the alpha particles were having high energy and were heavier as well. So if we say the atom is like a pudding of positively charged particles with electrons embedded in it, then the particles will pass straight through it. This is obvious because the heavier particles will pierce through the lighter pudding structure of the atom and pass through it. This is what Rutherford thought. For this reason, their greater mass and energy compared to the protons made him choose alpha particles for the experiment. Next, he used a very thin gold foil on which the alpha particles would bombard. Why did he choose a gold foil? Well, a really thin gold foil was estimated to contain approximately 1000 atoms. Lesser the atoms, more convenient the experiment would be. Lastly, are we able to locate this circular band with a gap here? What could this be? Well, this is the screen. A fluorescent screen that would help us detect the radiation. That means the screen will glow or emit fluorescent light whenever alpha particles will hit it. So this is how the track of alpha particles can be traced. Now we're all set to understand how the experiment worked. The alpha particles were emitted from the element present in this box. These directly hit the gold foil. Now what should happen ideally? As we know, the Thomson's model suggested that an atom is a sphere of positive charge with negative electrons embedded inside it. That means it is expected that the alpha particles will pass right through the atoms and hit the detector straight. And why so? Because the mass of alpha particles is heavier than the mass of positive charges. That means they should directly hit the atom and move ahead through it. Only a very small deviation would probably be acceptable in this case. But is this what he observed? Not really. He was astonished to get unexpected results. What results did he get? He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Based on the conclusions he had, he put forward the new hypothesis explaining the structure of atoms. Let us imagine that we have a ball made up of cotton. The cotton in the ball is very sparsely distributed and has an extremely tiny circle or sphere located at the center. This sphere is quite hard and dense. So hard that it can even resist a bullet shot against it. Now what will happen if you shoot many bullets across this cotton ball? Most of them will travel straight through the cotton surface. What will happen if a bullet hits the edge of the central heavy mass? In this case, the bullet will slightly change their path and get deviated. So looking at the size of the central mass, it's obvious that only some of the bullets will get deviated. Lastly, what happens when a bullet hits the center directly? Needless to say, it will bounce back. Because we know that the central dense mass is too hard for the bullet to pass through. So very few bullets will bounce back. This is analogous to what Rutherford had inferred about the atomic structure. His first conclusion was that most of the space inside an atom is empty. This is because most of the alpha particles could easily pass through the atoms and hit the detector straight. Now, if most of the space is empty inside an atom, then where is the positive charge located? Well, that's the second conclusion. The positive charge is compactly packed in a tiny entity. This occupies an extremely small space inside the atom. Now, why did he think so? Let's go back to our cotton ball and bullet example. Can you recall the second and the third case? Yes, the bullets get deviated on hitting the tiny sphere of the edge and they will rebound when they hit the center. Same explanation holds true for this. A few alpha particles get deviated. That means there is a possibility that these hit the edge of the positive center. Yes, and one more possibility is that they get deviated because the positive center repels the alpha particles as they're also positively charged. Also, a very small number of alpha particles rebounded. That means there is a possibility that these alpha particles had directly hit the positive center. But since the number of these rebounding particles is too small, it explains that the volume occupied by the positive center is also very small. If the space occupied would have been big enough, then the number of alpha particles bouncing back would also be greater. So let's say there are gold particles in the foil. He found that most of the rays pass straight through the atoms. A few rays change their path and get deflected. Lastly, very few particles bounce back. These results compelled Rutherford to come up with a new nuclear model. Let's have a look at the hypothesis put forward by him. Firstly, there's a positively charged center in an atom called nucleus. Nearly all the mass of an atom resides in the nucleus. Secondly, the electrons revolve around the nucleus in circular paths. Thirdly, the size of the nucleus is very small compared to the size of an atom.